Welcome everyone, and thank you for joining us today for our webinar titled Mountain Lab, Studying the Effects of Stress in Extreme Conditions on Human Physiology. This webinar is the second installment in our ongoing series, Advancements in Exercise Physiology, Sports Science, and Biomechanics. This is Andy Henton from Inside Scientific, and it is my pleasure to be your host for today's event. Our session is sponsored by 80 Instruments and will focus on the effects of tilt, exercise, and high altitude on the human cardiorespiratory and autonomic nervous systems. With us to present his research on these subjects is Dr. Trevor Day, Associate Professor of Physiology in the Department of Biology at Mount Royal University. Trevor holds a Bachelor's of Science in Neuropsychology and a PhD in Respiratory Neurobiology, both obtained from the University of Calgary. In his current position at Mount Royal, he teaches courses in basic and applied physiology and conducts research focused on the integration between the heart, lungs, brain, and kidneys in response to stressors including body position, sedentary behavior, and high altitude. Today, Trevor will share a number of research case studies where he and colleagues have investigated tilt, exercise, and high altitude hypoxia and their influence on respiratory sinus arrhythmia. He will show how this research found its roots in his lab, starting with the use of a novel lower body differential pressure chamber integrated on a tilt table and escalated, quite literally, to 5,300 meters above sea level at Everest Base Camp.
Great, thanks Andy for passing it along, and thanks to Inside Scientific and 80 Instruments for sponsoring this event, and for all of you for joining us here online. I'm Trevor Day, and I'm Associate Professor of Physiology at Mount Royal University in Calgary, Alberta, Canada. I know that there's some competing demands in your time today, including watching the season finale of the hit series America. So I hope that this will be at least approaching as interesting as watching that today. So thanks for coming along for the ride. Certainly I think it's important to thank everyone who should be thanked, and so I want to lead with this. And I say this often, so perhaps it might sound like a cliche, but it's the truth that science is a team sport, and we're nothing without our trainees, our collaborators, and our funding bodies. And so I just wanted to give a shout out to all of my trainees that were involved either directly or indirectly with collecting the data that I'm going to show you today. Many of them have gone into other graduate programs at other universities, including some of my collaborators' labs. So a shout out to say hello to those of you that are registered online, because I know some of you are. In fact, some of them are texting me right now from Nepal. So hi everyone. But also collaborators across the country and around the world have really helped me get on my feet with my own research program. Of course, our funding bodies are very important to help fund the work that we do. And of course, we can't do our work without research participants and ethics boards, and so they played a big role in helping us collect these data for the story I'm going to tell you today. Just to give you a bit of a background where I am, because I know some of you are from all over the place, I'm in Calgary, Alberta, Canada. This is a city of about 1.2 million people in southern Alberta, right in the sort of foot of the Canadian Rockies. So you can see that picture on the left, that's where I live. I live just across the river on the right-hand side, close to downtown. We can see the Rocky Mountains close by, and about 45-minute drive, and you can be along the Rockies, and that's a real appeal for those of us living in Calgary. You can see our nightlife picture there, and some architectural wonders that were recently built on the bottom right. So I work at Mount Royal University, a small undergraduate-focused university, about a 100-year-old institution that recently became an undergraduate university. The research endeavor is relatively new here, so it's an agenda I'm pushing pretty hard to get rolling. We have about 13,000 undergraduate students at Mount Royal and no graduate program. So all of the work I'm going to share with you today was carried out with the help of undergraduate trainees. So this is the Mount Royal Integrated Physiology Lab that I developed when I landed here. And I've got lots of interests, some of which stem from my training as a PhD student, where I trained in animal physiology and had to sort of make the switch to working with humans, which took me a couple of years to get on my feet, and certainly a lot of help from collaborators and students along the way. So I'm broadly interested in the control of breathing, so respiratory chemoreceptors, acute, intermittent, and chronic blood gas challenges, if we want to make it simple. I've recently got into cerebral blood flow regulation as well, so you can see on the right-hand side here there's a yellow box, and that's called a transcranial Doppler ultrasound unit. And so with that we can make measures of indices of brain blood flow regulation in response to various stressors. And then lastly, in some of the stories I'll be telling you about today, is responses to hypovolemia and tilt, things like brain blood flow regulation with body position. And I'm going to tell you a lot today about this phenomenon called respiratory sinus arrhythmia. So broadly speaking, I'm an integrative cardiorespiratory and cerebral vascular physiologist, and so what that means is I'm interested in how the heart, lungs, and brain talk to each other, and recently added kidneys to the mix as well. I won't have time to talk to you about that today, but certainly we've added some renal responses to high altitude in our recent trip. So my interests, generally speaking, are with respect to stressors, and those stressors can be, as Andy said in the intro, body position, sedentary behavior, a little bit of exercise. I'm not really an exercise physiologist, but I see it as a stress that we can use to elicit various responses. And my most recent interest is high altitude hypoxia. So I'll tell you a bit about some of those stressors and responses today. For those of you that aren't as familiar with some of these terms and acronyms, I know acronyms are difficult to track when people are speaking or when reading manuscripts, and so I got good advice that, from Andy that I should lay out some acronyms, and particularly for those downloading this afterwards as well. So some of this will be familiar to many of you, but ECG refers to the electrical, a measurement of the electrical activity of the heart, and from that we can derive heart rate, which is measured in beats per minute, so you'll see some of those acronyms. The oscillation in heart rate that I'll be talking a lot about today is called respiratory sinus arrhythmia, or RSA. I'll be using that acronym a lot. We can talk about changes in inspired tidal volume, so a big breath in is VTI. We can also talk about a test where we look at the maximum amount of air you can voluntarily move, or forced vital capacity. We also do blood pressure measurements, and so mean arterial pressure can be derived as an average of systolic and diastolic pressures. I talked about TCD already, transcranial Doppler ultrasound for brain blood flow, and from that we can measure various arteries in the brain. The most commonly measured one is the middle cerebral artery, or MCA velocity, and I'll show a tracing that shows some of that stuff today. Also, from the phenometer you can derive an index of cardiac output, but the reason I want to bring Q up, or cardiac output, is because I'll talk a little bit today about VQ matching. What that means is just a ratio between breathing, the air that you ventilate into the alveoli, and the perfusion of the lung, or the cardiac output from the right heart to the lung. So we call that VQ matching. Lastly, I know some of you are interested in gas measurements, and so I'll talk briefly about it entitled CO2, that is to say the pressure of CO2 measured at the end of each breath. And then lastly, at least early on in the talk, I'll be talking about tilt, and so when you see HUT, head up tilt or head down tilt, I'm referring to body position on a tilt table. So with that out of the way, I wanted to start with some recent innovations in the lab, and I should give credit where it's due. I had this idea of integrating a device that had various stressors, or can impose or superimpose various stressors on the body, one being a lower body negative pressure box, and you can see this box here on the right hand side, and the other being a tilt table, and this person is in 45 degrees head down tilt. And so one of my first trainees in the lab, Michael Timko, was very handy with tools and said that he had some ideas about how to build this device, and so he did it. And he's very handy with other devices as well, and has gone on to be an innovator with building lots of research tools. And Mike's online here, so hi Mike. So this device here superimposes tilt and LB&P stressors, and so this LB&P box, lower body negative pressure, can create a differential pressure across the wall. Here's the vacuum cleaner that basically sucks out of the box. You've got a manometer here to measure the pressure across the wall. A kayak spray skirt keeps the seal, and then we positioned it on a tilt table as well. And so we can look at various stresses that translocate blood volume to various positions in the body. The LB&P box moves blood volume to the lower extremities, and tilt can move it around up or down as well. So this device actually won an Alberta Science and Technology, or the Aztec Foundation, Young Innovator Award from Mike. And so on the left-hand side there was the Young Innovator Gala. There's my dean, there's another trainee, Lindsay Boulay, and there's Mike Timko there on the right. There's Lindsay in situ in the box drinking champagne. And we set up various signals to actually display to participants who would come by to watch our little demonstration. And there's a AVI Instruments lab chart, there's the TCD, and there's Power Lab. There's the lab chart open on a big screen. So that was a big CV tool for Mike. And actually recently, he just emailed this to me this week, and so I wanted to sort of advertise this, that Mike actually recently published an instruction manual on how to construct lower body negative pressure chambers. So it's in press now. I don't think you can find it. It's still in the proof stage, but you'll find it in this new open access journal called Facets. It's a Canadian open access journal. So check that out if you're interested in building these kinds of devices. We finally got the damn thing published as well. So where we characterize brain blood flow and cardiovascular responses to superimpose body position and low body negative pressure. We worked with a medical illustrator to basically draw that same picture you just saw. and we've had it published recently in Physiological Reports, which is open access. You can check that out online. Well, lastly, this project and building up various undergraduate involvement from an advanced physiology course to an independent project course to summer research and then publishing it, won the American Physiological Society and 80 Instruments McKnight Early Career Innovative Educator Award. There's Tony McKnight there on the right-hand side. This was awarded to me at the experimental biology meeting in Boston in 2015. And the reason I bring this up is not just to say, hey, I won an award, but really just to illustrate the beginning of my relationship with 80 Instruments. And so Tony McKnight was giving a talk at that meeting as well, and he is one of the co-founders of 80 Instruments. And so he invited me to a dinner at this meeting where I got to meet a lot of, I got to hobnob with the Goober Smoochers at the 80 Instruments banquet and met a lot of the 80 Instruments staff, and they took an interest in the upcoming altitude research expedition I was planning in 2015, and they wanted to come along and support the trip. And so the rest is history, as they say, and I'll tell you more about that as we go. So the phenomenon I'm going to talk about today is respiratory sinus arrhythmia. This is the fluctuation of heart rate in phase with the respiratory cycle. So just in terms of signal processing here, the top channel is the raw tracing from an ECG in lead 2 configuration. You can see the R to R interval here. That's one period or one cardiac cycle. Later on in the talk, I'll talk about R to R intervals. And from that, we can calculate, so it's just 60 over the period, we can calculate instantaneous heart rate. And notice here that in phase with the respiratory cycle, on the bottom channel, that's the respiratory flow, you get this transient fluctuation in heart rate. And so as you breathe in, everything above the line here is inspiration, everything below the line is expiration. As you breathe in, you can see that there's an increase in heart rate, and as you breathe out, there's a decrease in heart rate. We can use this peak-valley method to look at the magnitude of this oscillation from the top to the bottom. So that's the phenomenon I'm going to be talking about today, is respiratory sinus arrhythmia. Well, it's a powerful phenomenon because as your heart rate fluctuates, it actually translates to changes in blood pressure and translates again to changes in brain blood flow. And so this is a helpful slide to just show you a little bit about some more signal processing for those that are interested. So there's our instantaneous heart rate calculation from ECG. This is mean arterial pressure calculated from the raw phenometer input, so it's a beat by beat blood pressure input, and we process it using the mean in cyclic measurements. Here is the middle cerebral artery, the average middle cerebral artery velocity as well. And then from here, this is just the standard integral from the flows tracing to give you inspired volumes. And we put this dotted line here to show you the target that we'd ask participants to sort of breathe at. So each inspired volume is something like 1.3 liters here with each breath. And we're also monitoring carbon dioxide levels, so the end tidal CO2, the CO2 at the end of every breath. We're a little bit hypocapnic here from textbook values because we're in Calgary and they're instrumented with a face mask or with a mouthpiece, and so people often breathe a bit more and are a bit hypocapnic because we're at mild altitude in Calgary at 1,100 meters. But here you can see that as we have oscillations in heart rate, they translate to oscillations in blood pressure, and those translate to changes in brain blood flow. So it's actually quite a powerful phenomenon, this RSA. And so I'm going to talk to you firstly a little bit about what the mechanisms are that might drive RSA, some factors that may modulate RSA, and then lastly whether or not, and this is more of an evolutionary question I suppose, but whether or not RSA has any utility. Why does it exist in the world? And so starting with mechanisms, this literature, if I'm honest, is a bit of a mess and difficult to track. And the textbooks think that it's really, the textbooks sell it as being number 4, that changes in venous return. When I breathe in, I have an increase in venous return, I increase cardiac loading with the respiratory cycle, and that stimulates low pressure receptors in the right atrium. This so-called Bainbridge reflex was discovered in the 1920s by Francis Bainbridge in dogs with volume loading. Whether or not it's present in humans is controversial. But certainly there's a Bainbridge-like reflex that we see, which is respiratory sinus arrhythmia. Other hypotheses may be just that, starting with number 3 now, backing up, changes in blood pressure with breathing acting on baroreceptors, arterial baroreceptors or high-pressure receptors, or even stress receptors in the lungs and chest wall could play a role. And there's even evidence in reduced animal models that firing of respiratory neurons in the brainstem are impinging upon or impacting nearby cardiac vagal motor neurons as well. So there could just be a central mechanism driving this. And so we're not really clear on the mechanism that drives RSA, and so we wanted to investigate that a little bit using what I call the intact human model system. So I'll just briefly overview what the respiratory pump is. So the respiratory pump really is just how not only do you bring air into the chest cavity when you inspire, but you also suck blood into the chest cavity as well by improving venous return to the relative negative pressure of the chest cavity. So as the story goes, and this is the story the textbooks tell which drives RSA, is during inspiration you get an increase in venous return via the respiratory pump, an increase in atrial pressure in the heart, stimulation of these low pressure baroreceptors in the right atria and pulmonary artery, and then causing vagal withdrawal through so there's a feedback loop here at the brainstem. Vagal withdrawal, we know that the vagus nerve slows heart rate down normally at rest, and so if you have vagal withdrawal, you take your foot off the brakes and you increase heart rate. Similarly, when you expire, there's a relative positive pressure in the chest cavity that will decrease venous return, decrease right atrial pressure and congestion in the right heart, less stimulation of those receptors, and through that feedback loop, you can put your foot back in the brake, increasing vagal tone, and thus decreasing heart rate. And that's how the theory goes that RSA is driven. So those are possible mechanisms that mediate RSA, but there's also factors that modulate RSA, and they can be things like your age or your fitness level. We know that young, healthy participants have low resting heart rates and large RSA magnitude with the respiratory cycle. In fact, why don't you just try it now as you're listening. Just take your radial pulse and take a big breath in slowly, and you should feel your heart rate increase through that pulse. But things like respiratory frequency can also modulate RSA magnitude, blood gas levels as well, hypoxia, hypercapnia shown to have modulatory influences. There's implications that the nervous system activation might play a role, so we know that RSA is largely an index of the parasympathetic nervous system, the health of the parasympathetic nervous system, and so if you activate the sympathetic nervous system, it may dampen it. And lastly, because of the respiratory pump, as we talked about before, tidal volume can modulate the magnitude of RSA. So I'll just finish with talking about some possible utility of RSA. So why does RSA exist? Now there's some modeling work that suggests that it might improve cardiac efficiency in terms of energetics, making it less expensive to run your heart by oscillating the heart rate in phase of the respiratory cycle. Some think that it might improve VQ matching, ventilation perfusion matching. And so just to walk through the story in this middle diagram here, during inspiration, you fill the alveoli. This is when atmospheric air comes into the lung. You'll increase heart rate and thus increase cardiac output, perfusion of from the right heart to the lung, and thus you'll match ventilation with perfusion when you need gas exchange the most. When you exhale, or during expiration, you'll get a relative removal of air from the lung, and thus you'll slow the heart rate down and thus limit perfusion to the lung when you don't need it. And so you can see that RSA may actually play a role in gas exchange efficiency. And it's not clear if that's actually true or not. So I want to talk to you about the phenomenon of RSA during various studies that we've carried out in the lab and in the field. And so we'll talk about it in sort of 3 experiments, one in response to tilt, one in response to exercise, and then again in response to high altitude hypoxia. This picture was taken, that's Emma de Blom. This is in the Everest region, taken this last May. Okay, so let's start with tilt, first of all. So this is on the right-hand side is Trendelenburg position. It's often used as a treatment for people in hypovolemic shock. And so what we do know is that tilt causes a gravity-dependent redistribution of blood volume toward the central cavity if you're in head-down tilt. If you stand up, so head-up tilt or just standing, can translocate up to a liter of blood volume towards the lower extremities. And some of you that are more familiar with this might know that you've only got about 5 liters of blood. And so that's a 20% decrease in the amount of venous return. So that's pretty powerful as a stimulus. So we're fighting gravity all the time, and there's various mechanisms we have to try and maintain blood pressure. But if you go into head-down tilt, like the Trendelenburg position or the tilt studies we're going to do here in a second, that translocates blood into the central cavity, thus increasing venous return, increasing cardiac loading, and can increase cardiac output through the Starling mechanism, but also through the brain bridge reflex, if that's our explanation for RSA. And so what got me into this was some previous studies with tilt. And so when I first started working with humans, I collaborated with a colleague at UBC Okanagan, Phil Ainsley, and I took one of these tilt tables to the Okanagan, and we did a simple little study on brain blood flow regulation with tilt, and we published that in 2012 with Janelle Jelimis, his first author here. And I came back to my lab and did some more studies on brain blood flow regulation and respiratory control with tilt. And this is a picture of the lab before we had it renovated to take out these lab benches. You can see a power lab system here. There's the phenometer We've got the phenometer on the finger here to monitor blood pressure, TCD, ultrasound looking at brain blood vessels, and then this is a spirometry flow head so we can measure ventilation. And so we published some of these studies recently. Rachel Scow was the other first trainee I had in the lab, and she led the first study that we published in 2013, one on that's on brain blood flow. This is on respiratory control 2014, and Mike Timko again on various body positions on brain blood flow regulation. But one of the participants in this study had this really interesting phenomenon, and so this person just happened to be in 45 degrees head down tilt. This is a 26-year-old female triathlete, so quite fit, and was at 45 degrees head down tilt and was breathing deeply because we were giving some CO2 as a stimulus. So you can see here, actually it was Mike that noticed it in the NCA signal because we had sort of triplets. So you can see this relative clustering and scattering of ECG periods, and that translate into arterial pressure, and that translates into brain blood flow, as I said before. But interestingly, you get this big oscillation in heart rate, and so instantaneous heart rate can go from something like 38 to 110. That's a huge oscillation in heart rate that we noticed right away. So we stopped the protocol, we told her about it, we sent her to her physician and asked her to get it checked out. And she had a 24-hour Holter monitor performed, and the diagnosis came back that she had sinus arrhythmia, exactly the thing that all of us have. So this is normal and not pathological, and we wanted to make sure, of course, as well. So we looked at the ECG ourselves, and note here that there are P waves, and that's the red arrows here. And those P waves tell us that the electrical rhythm is starting in the right place. So it's a sinus arrhythmia, and it's not pathological. So we published this case report because we thought it was an interesting case of superimposed stressors of head-down tilt, which causes gravity-dependent cardiac loading, and deep breathing, which causes respiratory-dependent cardiac loading, causing this RSA phenomenon, this extreme RSA phenomenon. So I'll just lay out 4 raw traces from this paper. You can check it out here in 2014. We published this paper with Jeff Baden, one of my previous trainees leading this work. So on the top left-hand side, we've got supine baseline breathing. They're breathing tidal volumes about 1 liter or so per minute. You can see the respiratory cycle and the respiratory flow chasing. You can see sort of moderate RSA magnitude. Nothing out of the ordinary there. During deep breathing in the supine position, we're breathing about 2 liters a minute or so, 2 liters per breath, I should say. And then here you can see RSA maybe is a little bit larger, as you'd anticipate. Then when the participants moved into 45 degrees head down tilt, you can see here that doesn't seem to be any larger RSA when they're breathing sort of baseline levels, 1 liter or so per breath. You can see small RSA. But when you superimpose the 2 stressors, 45 degrees head down tilt, and deep breathing, again, you can see 2 liters or so per breath. There's the respiratory cycle, the flow tracing. You can see the clustering and scattering of ECGs really jumps out at you. And the calculation of instantaneous heart rate is between about 38 in some cases to over 110 in other cases. So that's pretty extreme respiratory sinus arrhythmia. The problem, of course, is this was in 1 participant. It wasn't a well-controlled study that was investigating the effects of tidal volume and tilt on RSA. So we thought we wanted to investigate this more closely to determine the effects of these various cardiac loading stressors to see if the Bainbridge reflex really was playing a role in driving RSA in healthy human participants. So our aim in a study we started in 2014 was to explore the relationship between the superimposed cardiac loading stressors, that being gravity-dependent, and that's the tilt-dependent cardiac loading, and inspiration-dependent or respiratory pump-dependent cardiac filling on the magnitude of RSA, as we saw in that case study. We hypothesized, like the case study, that we'd see some synergistic relationship between those 2 cardiac loading stressors. So here are our methods. We positioned participants in either 40 degrees head up or 40 degrees head down tilt. But before we did that in supine, we did a forced vital capacity test. This is just to see the amount of volume, of air volume that a participant can voluntarily move, and based upon that sort of lung capacity, we then did calculations of that forced vital capacity, 10, 20, 30, 40, and 50% of FVC. In case you're wondering how deep these breaths are, something like 15% turns out to be about your tidal volume. And so this is just below tidal volume at 10, and then 20, 30, 40, and 50 are above tidal volume. Now you can see this participant oriented in 40 degrees head down tilt on a tilt table. She has a pneumotac. This is a Hans-Rudolph pneumotac, or respiratory flow head. We've got gas sampling here, and on Douglas rack we've sort of taped a computer screen over top of her head so she can actually look at the screen and target those respiratory volumes like a video game. And so we'll show you what that looks like in a second. So we randomized 40 degrees head down and 40 degrees head up and compared the 2 within subject. So this is the kind of thing that we're looking at on the screen. So on the top here, you can see that a calculation of 20% forced vital capacity in this participant ended up being something like 0.7 liters. We call textbook levels for tidal volumes are about 0.5 or 0.6 liters per breath. So this is about 0.7, as you can see, and that dotted line shows you the target they were trying to hit. So people actually get quite accurate at it. So there's 5 breaths in a row. Thus you can see 5 different oscillations of RSA that we quantified using the peak value method. Here in the bottom tracing, just to compare, and is 40% of forced vital capacity. In this case, the tidal volume or inspired volume is something like 1.3 or so liters, so a lot deeper as a breath. You can see as those breaths are targeted, there's much larger magnitude of RSA. And again, the peak value method quantifies the magnitude of that. So we did a couple of things. We wanted to see what is the relationship between every single inspired volume that we measured and every single RSA, corresponding RSA magnitude. So we ran a correlation on that. I'll show you that next. But we also plotted RSA magnitude against the percent FVC, so we could cluster the data for each participant together, because we basically normalized the tidal volume to the participant's lung size. So here's the correlation analysis on the left-hand side. On the x-axis, you can see actual tidal volume between 0 and 3 liters or so, and here's the RSA magnitude. You can see, fluctuating between none at all, upwards as high as 35 beats a minute, if you can imagine how big that oscillation is. And that correlation came out statistically significant with an R value that's moderate, about 0.64, and highly significant. In 40 degrees head down tilt, for reasons I'll probably allude to later on, you can see the correlation is not nearly as good, but still moderately positive correlation, 0.53, and still highly significant. So there is a relationship between inspired volume and RSA magnitude. When we plotted it against the percent FVC, so we could cluster it together for each person at 10, 20, 30, 40, and 50% of FVC, you can see that these responses are highly linear, with an R-square value of this linear function being 0.99. And it looks qualitatively similar in terms of slopes for 40 degrees head down tilt as well. Recall what our hypothesis was, though, that we thought in head down tilt, this middle graph here, we would have a steeper slope. That was our anticipation. But that didn't come out to be the case. These are adventures and negative findings, or findings that you wouldn't expect. So you can see here we've got in head up tilt, the average is the gray bar here. Every black point is an individual participant. You can see the average is about 0.43. Here in head down tilt, the average is more like 0.33. Not a huge effect in terms of magnitude difference between the two, but statistically significantly different just the same. And so this is opposite to what we hypothesized. We thought that this would be larger. And so that remains to be explained. And so we think that it's probably because of the head down tilt position is stressful. So let me just summarize what we found. RSA magnitude increases linearly. So this is a new finding. This is a new method we've developed of this RSA reactivity slopes. We can calculate the slope and the magnitude of that response. However, that reactivity slope is not increased with head down tilt as we anticipated. In fact, it's the other way around. And that's probably because of the stressful position of head down tilt. Probably increases sympathetic nervous system activation in that body position. And so we asked ourselves, can we test this RSA reactivity during another stressor that both increases sympathetic nervous system activation and increases venous return in a big way? So instead of tilt now, we move toward exercise. So during exercise, we know the sympathetic nervous system is activated, so that's well established and clear. And we know there's a really big increase in venous return because of the skeletal muscle pump. And so I wanted to talk a bit more about that. So here's just a schematic of the skeletal muscle pump here. On the right-hand side, you can see in position 1, this person has their foot flat, and there's just this regular amount of venous return because of the respiratory pump and venous valves. This is a low-pressure system, so we're fighting against gravity to get blood back to the heart. When you contract skeletal muscles, those muscles will squeeze the veins, and because of the squeezing and those unidirectional valves, you increase venous return. And that's something that happens during exercise to recruit more of the pooled blood. 60 to 70% of your blood volume is in venous pools in gravity-dependent locations at rest. And so you can recruit more venous return and thus increase your cardiac output to meet metabolic demand during exercise. And so our aim of this next experiment was to explore the relationship between superimposed exercise stress that has the skeletal muscle activation and the sympathetic nervous system activation, and this inspiratory-dependent cardiac filling that we told you about earlier, that RSA reactivity. We hypothesized that sympathetic activation would win, that it would blunt RSA reactivity despite the increase in venous return from the skeletal muscle pump. thus the Bainbridge reflex is probably not as powerful as we anticipate, and that's our hypothesis. So here's our setup in the lab. We used a standard cycle ergometer where we could fix the work rate. Here are participants sitting on the bike. You can see our transcranial Doppler ultrasound, our AD instruments, power lab system, the phenometers down here, and also attached to the finger for blood pressure measurements. We've got a Hans-Rudolph respiratory flow head here. We're sampling gases. And this participant is looking at a computer screen for that feedback control. You can barely see it here, but you can see that sort of pink line we set there. You can do that in a lab chart where you expand out the respiratory, the inspired tidal volume channel and get the participant to target those volumes like a video game. And so we could repeat this experiment during moderate work on the exercise or then just at rest sitting on the bike. So here's our protocol. We brought them in first to do the exercise trial, and I'll tell you why in a second. This is led by Laura Lavoie, and Gary Saran worked closely with her as well. And they're going to be featured again as we in the upcoming altitude work that we'll show you as well. By the way, I should mention her name. Marie Brosimova led the work on tilt and RSA magnitude, and Jeff Baden played a role in collecting some preliminary data. So those manuscripts are in progress, and of course Marie is chewing her nails off to get that work out. So hopefully this talk will be a catalyst for that. So here's our protocol for the exercise study. We had a resting baseline of 5 minutes, and then we started exercising at a fixed rate of 100 watts at 50 RPMs. So there's a 10-minute exercise period. At the end of that 10-minute period, once steady state is achieved, we just look at how deep they're breathing. What is their voluntary inspired volume? What are they choosing to breathe at? And we basically normalize to that. And so we calculate what minus 15 is from that, because these are big volumes, right? They're exercising. Minus 15 of that, which is quite difficult to do when you're exercising. 0, so exactly what that is, plus 15 and plus 30. So we use those numbers as tidal volumes, inspired volumes, just like the tilt study. And we could target various volumes and look at RSA magnitude. We brought them in the next day and did a resting control. And so here they're sitting on the bike for 10 minutes. We use these same numbers, and so now they're resting, breathing quite large volumes now. And these are exactly the same volumes, so we can compare these volumes and the relative RSA magnitude between participants. So these are some raw traces. Here's at rest. You can see here inspired tidal volume. They're targeting about 1.7 or so. There's 5 cycles, and you can see a really nice RSA magnitude there that we can quantify with the peak valley method. And then during exercise, of course, the heart rate is higher during exercise, so there's sort of potentially a saturation effect here. But you can see targeting these same volumes during exercise between rest and exercise here, and there's just really hardly any RSA whatsoever. And so when we quantified it for each person, you can see here on the x-axis during rest, there's minus 15, 0, plus 15, plus 30. Not as linear as we saw with the tilt study, but relatively linear. And when we calculate those slopes, we saw there was a response as we anticipated during rest. During exercise, though, there is some RSA, about 4 beats a minute on average or so, with a pretty tight error bar there. You can see here, as we increase the inspired volumes, the response slope is flat. And so there's just no RSA reactivity. And so our hypothesis was correct that during times of stress, like exercise, there is no RSA reactivity, despite the fact that for each breath, there's probably a larger venous return because of the skeletal muscle pump in the background during exercise. So then we quantified it. And so each of these black points is a single individual. The gray bar is the mean of that group. Here, with the exercise here, the mean is actually right around 0. And so basically, there is some RSA, but the slope is abolished during exercise. So to summarize, we do have a little bit of RSA during exercise. However, the reactivity slope through this new method that we worked out with Marie Brosimova in the tilt study, it's eliminated during exercise, despite increases in venous return. And that's probably because the sympathetic nervous system wins in terms of blunting RSA. So we had another question then. Now that we learned that the Bainbridge reflex probably isn't that powerful in humans, and the sympathetic nervous system will modulate RSA or even blunt it if it's powerful, then can we go into another context whereby the sympathetic nervous system is turned on? So we thought that perhaps the RSA would be affected by acclimatization to high altitude hypoxia. And we had a second question as well, whether or not the magnitude of RSA will affect VQ matching, and in the case of being hypoxic, should improve your oxygenation if that's true. Perhaps this is the reason you've all come today, but I wanted to talk a little bit about some studies that we performed, or at least one study that we performed at high altitude in May. And I know some of the listeners online right now are either in Kathmandu, having just come down from Everest Base Camp area, or have actually just returned to Canada following some trips. So hopefully you'll find this interesting. And those that have never done this kind of work before, I hope you find it interesting as well. This is now, in my view, some of the most interesting work that I get to do, and I really feel lucky that I get to do this for a living. So this is obviously Mount Everest along the border between Tibet and Nepal. It's the highest summit on the planet. You can see here right in the middle at just under 30,000 feet, or just under 9,000 meters if you're using metric. The atmospheric pressure here is about a third of that sea level, so it's about 250. The available oxygen is about 33% or so. So this is the south side of Everest taken from an airplane. So I want to talk a bit about high altitude. So as you just mentioned briefly, the physics and the issue with high altitude is the reduction in available oxygen as you ascend. So many people think that the percentage, and this is what students often think, the percentage of O2 is lower as you ascend. That's not true. The fraction of inspired O2 is the same as you ascend. It's the pressure of the available oxygen that's lower. And so we'll just start with this dark line here in Vancouver, just because I'm Canadian, is at sea level. You can see here about 760 millimeters of mercury. And then as you ascend, Calgary is about 1,100 meters. An airplane cabin is pressurized to the equivalent of about 2,400 meters. And just above Everest Base Camp, 5,500 meters, there's half the available oxygen of sea level. And so you can see here 760 up high, and as you ascend, the atmospheric pressure drops. Well, 21% of this, that's the FiO2, the fraction of inspired O2 is always 21%, no matter where you are, is less here, so about 160 in Calgary. You can see here at Everest it's about 50 or so, about a third. So that's the problem with high altitude. This is a small little chapter I wrote for Pearson Education if you wanted to look up this reference and download the slides afterward. And so here's our third experiment I wanted to discuss with you today, was to explore this relationship between superimposed high altitude hypoxia as a stressor and this inspiration-dependent cardiac loading that we talked about so far today. So our first hypothesis was that in the increase in sympathetic nervous system that we know is the case during high altitude hypoxia will reduce RSA magnitude similar to our exercise study that we showed you before. But our second hypothesis took the sort of utility of RSA question further, whether or not those that had large RSA would also have improved oxygenation through improved EQ matching. So those were our questions. So I want to tell you a little bit about the trip and a bit about the Everest region in general, just as a general interest thing to set up the story. This is Everest Base Camp. This picture was taken this last May. Everest Base Camp is just a tent city that gets set up on a glacier. The Khumbu Valley Glacier, the Khumbu Glacier basically comes to an end and takes a right-hand turn and goes up a hill and becomes the ice fall, the beginning of the Everest climb. So the Everest Base Camp trek ends where the Everest climb begins. So this is Everest Base Camp here, and there's always a cairn set up to sort of mark it, and so we've got a picture of our group sitting here. I'll show you at the end. So this is Everest Base Camp. It's located about 5,300 meters or so. It takes about 12 days to get to from a small village called Lukla. It is about a 60-kilometer walk. So I get asked this all the time, why Nepal? Some of you probably know that Nepal experienced a devastating earthquake on April 25th, 2015, and some terrible aftershocks a few weeks later. We actually planned to go in 2015. I had a group of 17 people ready to go. We paid. We had our Sherpa guide team in place. And we're about to leave on April 25th, a week before departure. The earthquake happened. At least 9,000 people died in the Kathmandu Valley. 19 people died at Everest Base Camp because of a small piece of, probably a large piece of ice that fell off a nearby mountain called Lintrin and washed across the base camp. And so a lot of uncertainty arose about Nepal as a destination. I can tell you, having been there, and some people are online who just got back from there, it's safe to go to the Everest Base Camp region. There are parts of Nepal that are not okay, but this part certainly is. So why Nepal then, with all this uncertainty from the previous earthquake? Well, I had previous experience there. So in 2012, I went with an expedition to the Italian Pyramid Lab that's close to Everest Base Camp, with an expedition led by Dr. Phil Ainsley at UBC Okanagan, and actually Mike Timko came along on that trip as well. And so we were lucky enough to be involved in this large expedition. So I learned a lot, made connections, and you can't overstate the importance of having good connections in developing countries when you're trying to do this kind of work. So that those local connections bring the cost down per person when you're trying to organize these kinds of trips. Now, Everest Base Camp is a bucket list destination that people will self-fund to go to. So if you're going to a lab somewhere at high altitude to work for 3 or 4 weeks to look at acclimatization over time, those are expensive trips because you need advanced trainees, postdocs, PhD students, master's students, and they all require salaries. So those are very expensive trips. So this is a way to get the cost down where people will self-fund to this bucket list destination and then give up their bodies for science to help you out. Everest Base Camp gets quite high, so 5,300 meters, but you get there really slow over about 12 days or so. So the risk of getting acute mountain sickness is reduced because of that. There are no technical skills required. You're really just walking on trails like this and outdoor running shoes, and so there's nothing technical. There's no, other than a rare earthquake that happened in 2015, there's no objective risks on this trail all the way up. It's really just a long walk on trails. You stay in lodges. You're not camping. There's power in the lodges, and there's rest days built in along the trip, and so you've got opportunities to make measurements as you ascend. And of course, the Nepalese people are amazing to work with, and many have become good friends of ours. And Everest and the mountains around it are some of the biggest in the world. So there's lots of appeal to this area. So there's our Raiders of the Lost Ark treasure map that shows you the Everest Base Camp trek. We start in Kathmandu. We fly to an airport called Lukla. If you're getting a bit bored and want to distract yourself on another screen, then perhaps pull up YouTube and plug in Lukla, and you'll see some videos of landing in the most dangerous airport in the world, and I'll show you a picture in a second. From there, you start the trek up to Manjo, to Namche. We went to Tengboche, to Ferroche, Gorek Shep, and lastly Everest Base Camp. That Italian pyramid lab I keep talking about is found here just outside of Wolfsche. And this little summit here called Kalapatar, a nice little scramble that people can scramble up as a final destination above Everest Base Camp, where you can see across the valley to Mount Everest. So I just wanted to make a comparison of altitudes here. Some of you might be familiar with Banff, the Banff National Park, just west of me. So Calgary is sort of off in the distance. This is the Bow Valley. All of these mountains along the Bow Valley are somewhere between 2,600 and 2,800 meters. This is the township of Banff itself. This is a mountain called Mount Rundle. It's a very long mountain that goes between the town of Canmore and Banff. And you can actually scramble to the top, the east or the west end of Rundle. Banff here is about 1,400 meters in elevation. The top of Mount Rundle here, we'll call it about 2,800 meters in elevation. Just as an equivalent, Kathmandu is a city where you start, where you land, is about 1,400 meters in elevation, just like Banff. And the airport at Lukla you fly into is about 2,800 meters. And that's where you start the Everest Base Camp trek. So one of the highest areas, there's larger mountains in this than the Canadian Rockies, but all these are on average about 26 to 28. That's actually where you start the Everest Base Camp trek. That just gives you a sense for scale. So in May 2016, I put a new team together after the disappointing cancellation of the trip the previous year because of the earthquake. Recruited 23 participants, including 9 paid trainees from Mount Royal. That was no small grant writing endeavor. Lots of collaborators from various institutions around the world and some industry partners. So we brought 80 instruments along, 2 people for 80 instruments, and they also lent us some gear as well. And then some community members from across Canada, US, New Zealand, and Ireland as well. So Kate Mikes from USA was on the trip from 80 Instruments, and James Elworthy from New Zealand from 80 Instruments came along as well and helped with lots of pictures and videos for us. We got ethical clearance from my research board at Mount Royal as well as the Nepal Health Research Council. We thought it was important to play nice in the international sandbox and the local sandbox in Nepal as well. So our objective of this trip was a fast and light approach to high altitude acclimatization on a trek to Everest Base Camp, and we had various studies that we did. So here's the Pelican cases, and we'll sort of follow the Pelican cases today. Here's our 5 Pelican cases that we loaded up from the lab, and this was on April 29th, the day before we left. From there, we hit the airport. I didn't believe we were going to go until I got on the plane, just given the disappointment of the cancellation the year before. So there we are with a box of consumables and a couple of Pelican cases at the Calgary airport the next morning. So here's our ascent profile. We did baseline measures in Calgary, I should tell you that. At least for the RSA study I'm going to tell you about today. So we did do a baseline measure in my lab in Calgary. We then in Kathmandu for a couple of days to get organized. We then flew up to Lukla and trekked to Manjo on the first day. We had a rest day in Namche, a rest day in Tengboche, and a rest day in Ferroche, and then up towards our Everest Base Camp objective, which is just past Gorek Shep, if you recall, and then a descent back down again. So the measurements that we took were in Calgary, here on a rest day in Namche, here in Tengboche, and here in Ferroche. And so relatively equal ascent profile altitude changes, Namche at 34, Tengboche at 38, and Ferroche just over 43. So here's a picture of the Lukla airport. If you haven't Googled it already, a very short runway. I think it's under 500 meters. There is a ledge here that the pilot has to sort of miss and land on and then stop abruptly. There's the tower, and this is the airport at 2,800 meters. So a pretty thrilling place to land or take off from. This is actually a small village as well. There's a little shopping area, lots of lodges to stay in, and this really is the beginning now that this airport was built by Edmund Hillary, this really is the beginning of the Everest Base Camp trek for most people. So this is just a walk on trails, really. There are 13 suspension bridges along the way. They were not damaged by the earthquake in 2015. This is our group here this last May. We're trekking with small light packs with maybe our laptops and some clothing and water bottles and things like that, some snacks. Everything else is carried with various beasts of burden, carrying our duffel bags and Pelican cases. So you can see a couple of Pelican cases here being carried by a horse, and then some humans did it too. So this is Kanji, one of our porters. We had 5 porters that were hired. This is Nima, our lead guide. And you can see the difference between what a guide carries and what a porter carries. Just for reference, this is about 50 pounds, this Pelican case. And then, you know, on top of that, three duffel bags. And so they're paid by the kilo, and so Kanji kept asking for more weight, more weight. They really are amazing people, and physiologically speaking. And so just to tell you a bit about what we did, we focused on some daily measures in Nepal between 6 and 8 a.m. every morning. You can see here on this participant's finger we've got a pulse oximeter for heart rate and ECG, sorry, heart rate and oxygen saturation. This capnograph for end-tidal CO2 and respiratory rate. We took blood pressure measurements. We took acute Mount Sickness scores. We had accelerometers here for daily measures of physical activity as well as sleep disturbances. Everyone's got sleep apnea up there, but that's another story. We collected these data on the ascent and descent, all the way up and all the way down on 21 people. On rest days, we did another series of experiments. This was between about 10 a.m. after breakfast and about 5 p.m. And we really just set up in bedrooms and lodges in the hotels that we're staying in along the trail. So you can see here we've got a participant seated at a dinner table. There's a power lab system and a laptop. Participants instrumented for various respiratory tests here. So we looked at hemoglobin and hematocrit, some renal reactivity measurements using urine, some breath holding, some ventilatory acclimatization, and some RSA reactivity, which I want to tell you about today in a smaller group of people. So just to show you the area, this picture was taken in 2012 when I was there. There's the lodge there we stayed in 2012. This is the sort of administrative capital of the Everest region, Namche Bazaar, big shopping area, lots of coffee shops and restaurants and places to buy gear and candy as you load up before you head up further up. So the view in Namche is beautiful. This is the picture out of my bedroom this last May, just to give you a sense. This is an amazing place to do research, so please email me if you want to come next May. So this is us setting up in the bedroom. This is my bedroom in Namche as one of the labs. We took a power lab out of its Pelican case and used it as a table, had a participant sit in a chair here. There's Jamie Foe, Kennedy Borley, Lauren LeBlanc, Michelle Brandt, and Nikki Bruce, some of my trainees helping out with this. From there we do another rest day in Tengboche. Here we are now set up in a lodge dining room where we have a participant instrumented. We had another power lab system here, so we had 2 stations set up to get 12 people through in a day. And just to give you a sense for what our sort of days look like. So again, remember there were 3 rest days, Namche 34, Tengboche 38, Ferrochet 43. But we just set up in lodge dining rooms where we had power, and the lodges are pretty empty during the day, so we had the place basically to ourselves. One of our participants set up a GoPro camera in the corner just to kind of video us instrumenting people. There's a lab chart, power lab system here. It's a power lab system over there. We've got 2 tables. You can see James Elworthy from 80 Instruments and taking a bunch of video here as well. So that's basically what our rest days looked like on those 3 occasions. There we are in Ferrochet, just to give you a sense for the sort of relative chaos of our systems, but this made sense to us. We'd set it up the night before, unpack it, set it up in the dining rooms, plug it all in, and off to the races we went for data collection. Here we are in Ferrochet collecting data with our power lab system and a laptop. And then lastly, data collection was finished in Ferrochet. So this was our 3rd rest day, and so I took pictures of the 2 stations as we were celebrating the end of the day when we got the data collection for the RSA studies finished. So I want to introduce a new concept, a new mathematical principle I haven't yet before. And this is another way of looking at heart rate variability, or RSA magnitude. This work is being led by Gary Saran, and Lauren LeBlanc helped pretty closely with this as well. This is analyzed through the LabChart Pro heart rate variability module. So this is actually quite easy to do with LabChart Pro. So here we plotted every R to R interval, every cardiac period. And against it, we plotted the next R to R interval right beside it. And based upon stacking everyone's ECG from about 7 minutes of baseline end to end, we could plot everybody's R to R interval against this next R to R interval and get this plot called a Poincaré plot. And from that, you can get various indices of the magnitude of this. This axis, long axis here, is the long-term variability. That's ST2. This short axis here is ST1. That's the sort of short-term variability. That really is RSA. If this was to be fat, you'd have larger RSA. So that's another way of quantifying RSA magnitude. So here's our 4 Poincaré plots for Calgary, Namche, Tengouche, and Fariche. Qualitatively, they don't look that much different, but then we can quantify them. And you can see here the SD1, SD2 ratio is about 0.4 to 0.5, and statistically speaking, there's no difference between them. So it looks as if RSA magnitude, at least during spontaneous breathing, isn't any different as we ascend in altitude. And that was a surprise to us, given our expectation that the sympathetic nervous system would dampen RSA magnitude. So then we also use the peak valley method, the respiratory coaching that we saw before. You can see this sort of increase in inspired volume. Here we're targeting about 1.55 or so as a volume, 1.5 liters, and so there's an inspired volume, there's an RSA magnitude, and it's quantified via the peak valley method as well. So just by calculating slopes, as we said before, here in the top right in Calgary at 30% FVC, 40% FVC, and 50% FVC, very similar to that tilt study we talked about before, we can calculate the slope. But again, qualitatively, those slopes don't look that much different. We also looked at the 50% FVC as well. So when you're breathing the deepest, what is the RSA magnitude? And it looked like, we're about 22 here, and then in Namche, you're down below 20. So it looked like you actually had a reduction in forced vital capacity, so perhaps these slopes just shifted down. So we looked at both the slope and the absolute magnitude of RSA at 50% FVC. So here we are quantifying them. This is each altitude. Here's the RSA slope, just like the tilt study. You can see here about 10 beats per minute per liter. Again, no statistical difference between those slope calculations. And lastly, when we look at the RSA magnitude at 50% FVC, it looks like there might have been a trend, but statistically speaking, because of all of the variability here, there's no difference between the RSA magnitude at 50% FVC at each altitude. So I want to talk a little bit about hypoxia, and just to kind of wrap up the story today. This is a pulse oximeter I took with me to bed in Gorak-Shep, just under 5,200 meters. There is something about 5,000 meters as a threshold. People really started to feel worse, and oxygen saturation really started to go off a cliff. So there was my oxygen saturation at 79%. I'm lying in bed at night in Gorak-Shep. We just arrived. My heart rate at resting is 95. If you were in healthcare and you saw these numbers, you'd hit the alarm, right? So here's just to give you a sense for what happened to our saturation. This is a group of 21 people, starting in Kathmandu, over 96% in Kathmandu. And as we ascend up towards Everest Base Camp, remember Everest Base Camp is beyond Gorak-Shep, we got down upwards of on average around 82 or so. I was a little lower than that. So that's what happens to oxygen saturation as you ascend to Everest Base Camp. And so because of that, of course, people can get acute mountain sickness as well. But the interesting problem we have here is that because they're hypoxic, perhaps RSA magnitude can help improve oxygenation when you're already hypoxic. So just to remind you of this VQ matching hypothesis, people think that as you inspire, you have an increase in heart rate, that's RSA, and you increase the Q, or the perfusion of the lung, thus improving VQ matching for gas exchange. This should improve oxygenation if this hypothesis is correct. So we tested that hypothesis as well by correlating the resting RSA as quantified by SD1 or SD2 in Fariche when they're hypoxic, and looking at their oxygen saturation, and there's no relationship. So there's no relationship in these 12 people between resting RSA magnitude as quantified by the Poincaré plot and their resting oxygen saturation. Similarly, we wanted to see if breathing deeply, that's at 50% of FVC, breathing deeply improved their oxygen saturation. So what's the RSA at 50% FVC? Does that correlate in any way to the improvement of oxygen saturation during those deep breaths? And you can see that people are somewhere improving maybe 2%. Some people improve like 7 or 8% their saturation while they're also in Fariche. And you can see there's no relationship here as well. So it looks as if the VQ matching hypothesis doesn't hold either. So just to summarize these experiments, resting RSA magnitude is unchanged with acclimatization via Poincaré plots. That's while just breathing normally at rest. RSA reactivity, that's sort of driving RSA with changes or targeting inspired volumes, those slopes are also unchanged with high altitude. And lastly, no matter how you look at it, RSA magnitude does not improve oxygen saturation in the context of high altitude hypoxia, suggesting that VQ matching hypothesis is not correct either. So just to finish the story of high altitude expedition this last May, off we went once we finished our data collection to Everest Base Camp. This is Lauren Lavoie. She often joked that she doesn't even like hiking. Somehow I managed to talk her to coming to Nepal with me, and off we went to Everest Base Camp. There's our group at Everest Base Camp, all 10 of us. Kartika here is a prof at Mount Royal who came along to help, and the rest are paid trainees from various universities, but all paid through Mount Royal this last summer. The ice falls are just behind us here, so this is a really great shot that we got. Some people scrambled up to the Kalapatar summit. It's a nice objective to just sort of see the valley. This is the famous mountain Pomorian behind, pyramid-shaped mountain, about 7,000 meters or so. There's most of our group. Some people stayed behind because they weren't well, but this is the next morning. Up we went to the summit. There's Kate Mikes from AV Instruments. James Elworthy is back here as well from AV Instruments. I'll find him. There he is right in the back. There's our lead guide, Nima Sherpa, and a couple of other guides, Calden and Tashi Fura. And so it's really important to have a great team for this kind of work and to have some fun, because this objective was really important to people to see this view. And there's the view. So you can see here there's Everest, the base camp is down below, there's the ice falls at the beginning of the climb, and there's Everest there. So that's the view taken from that location. Pretty amazing experience. I just wanted to remind everyone that there are risks associated with this kind of work, that acute mountain sickness is a real risk. This participant, this is taken at Everest Base Camp. We took a couple of hours to get there from Gorak Shep and walked around, and he just said, I'm just so tired, and he lied down, as a joke. But later on at dinner, he was lying down at dinner as well, so he really wasn't feeling very well the rest of that day. One of our participants needed to be on oxygen therapy the next morning before we left, and so these kinds of things are important to think about, that they do come with some inherent risk, and you have to stay on top of that. Then we descended over a couple of days and ended up back in Lukla. So here's the streets of Lukla. The airport is just over here. Lots of shopping if you wanted to. And there we are finishing the Everest Base Camp trek and celebrating. Of course, all the comforts of home in Lukla as well. Is there anywhere where Starbucks isn't? So there we are. There's a Starbucks in Lukla if you want to. And we did spend some time hanging out there afterward. And there we are at Lukla Airport with all of our gear, some of our Pelican cases. Astonishing to me that they came from Calgary, landed in Kathmandu, were flown up to the Lukla airport in small airplanes, carried up on the backs of humans and various animals to help with the expedition, brought back down to Lukla, and there they are, and then made it to Kathmandu. So there's our 5 Pelican cases and 1 from another university, and safe and sound in Kathmandu, and then safe and sound in Calgary. This is the last picture I took as I was waiting to get picked up at the Calgary airport afterwards. So the Pelican cases have come full circle. I'll just finish by talking a little bit about some comparisons between research in controlled laboratory conditions and research in austere environments. And really, in the end, it's a balance between doing work that is novel, or else what are we doing? We're just doing teaching demos otherwise. And those are important things to do as well. But if you're going to do research and try and disseminate it in some peer-reviewed fashion, then you really want to try and aim at doing some novel work. But it also has to be feasible. So it's much easier to do feasible work in a lab. So feasibility is a lot less in high altitude context, but it's more difficult to do novel things. And so you've got to think hard about, what are some holes in literature, what are some skills that I have, what does my team bring to the table. And here's a picture of Gary Surratt and Lauren Lavoie setting up a power lab system in Tengboche the night before we were going to do a rest day measurements the next day. Here's my lab in Calgary, transcranial upper ultrasound, power lab system, phenometer, dentist chair, nice stable environment with which to work. If you're going to do this kind of work, it's so important to build the right team. We had a great group of Sherpas. Sherpa, by the way, is not a job description. It's an ethnic group. They just happen to, many of them work in tourism. This is Nima Sherpa, who's our lead guide. He's become a very dear friend now, and has done a lot to help us over the years. It's important to think about being well organized ahead of time. It's important to think about the safety of participants as well, and to manage the expectations of both the people who have self-funded to go, who have an expectation of their experience, but also the needs of the research in terms of collecting the data. And that's a constant balance you're always trying to find. It's important to think about the culture in which you're working, so having some sensitivity to the culture, thinking about some interpersonal perspectives. Every single one of these people had a goal and their own personal experience. This is the Italian Pyramid Lab, by the way, where we spent 3 weeks in 2012, and some of my friends just got back down from recently. So the best advice I got from Phil Ainsley, my collaborator at UBC Okanagan, before I left was, Trev, no matter what happens, stay positive and optimistic. And that became some of the best advice that I got. And I added to that, keeping your sense of humor as well. So we thought we were awfully funny all the time. Perhaps the first 3 points here aren't terms you think about with respect to science, but being creative, improvising, looking for serendipitous opportunities to try new things. Of course, you all know this in science you have to be persistent, but perhaps finding compromises in terms of what's feasible and what's novel. Lots and lots of problem solving. I learned a lot about problem solving in this condition and being responsive to new opportunities. And just expect the unexpected is going to happen. We're constantly solving problems. This is one of the labs we set up, and we did some urinalysis and hematocrit measurements here. Where's the plug-in? So we have to think about things like power. We have to think about things like the limitations of your gear and what's feasible. And lastly, I just wanted to give a shout out to working with undergraduate students. Many people in science work with more advanced trainees than I do, so we train master's and PhD students and postdoctoral fellows, and those are important initiatives to keep the endeavor going long term. But lots of people don't think you can do work that's publishable with undergraduate students, but I'm here to tell you that I have a federally funded lab now, and I've worked with truckloads of undergraduate students. Many have gone on to graduate programs elsewhere, and they're still friends and collaborators. So you can do it with, if you're careful with your questions and your training, you can work with groups of undergraduate students who are very smart, very ambitious, very keen, and work great in teams. And so I have nothing but admiration from the students that I take on, and I can't thank them enough for the work they've done with me. Also, just to say thanks to Nima and his wife Ang. Ang was pregnant in this picture, and this last July gave birth to a healthy baby girl. So these are good friends of ours now. This is us saying goodbye in Namche on the way down. And then there's the whole team that made this happen. And it's a really special experience to be part of expeditions with friends like this.
Trevor, you made a reference to acute mountain sickness. How do you watch for that, and did any of your group experience this in Nepal?
Yeah, that's a good question. It's something I alluded to along the way, and something that you're, sort of expecting and anticipating, but terrified of. I know there's a slide we put in, Andy, if you could throw that up. Thanks. This is a handout I made that's based upon the acute mountain sickness score. It's the Lake Louise scoring system that was created in the early 90s at the Lake Louise hypoxia meeting. I should say that we're rethinking this a little bit, and there's some questions about whether or not we should include sleeping difficulty as a part of the score, which is why we've added up in different ways here. But I'll just mention some of the symptoms of acute mountain sickness. And the most common one is headache, and our scale goes from 0 to 3. Again, not a very sharp knife. Gastrointestinal symptoms. Of course, if you're traveling in a third world country, many people know you get traveler's diarrhea. I've heard it said that in Nepal you either have traveler's diarrhea or you're about to get traveler's diarrhea, so it's one or the other. And that's not what we're talking about here. This is other gastrointestinal symptoms like nausea, vomiting, bad appetite, anorexia, and so 0 to 3 on that as well. And it's difficult to tease apart those two different things, and so that's why this instrument is really a self-reporting instrument. From there, we can move to fatigue or weakness. This is one I experience a lot, including lightheadedness and dizziness too, so 0 to 3 on both of those scales. And then lastly, difficulty sleeping. I should say that everyone has sleep apnea up there to varying degrees, and so difficulty sleeping may not be a symptom of acute mountain sickness, but rather is just a normal part of acclimatizing and having cranked up carotid bodies in terms of respiratory control. And so we're rethinking this, but this is a self-reporting scale. It's the best tool we have to get a sense for how people are feeling as they ascend. The score is out of 15. Anything over 5 is considered acute mountain sickness. And of course, it's a bit of a blunt instrument, but it does give you a sense for how people are doing. We had quite low numbers all the way up, and I'll tell you why in a second, at least why I think we did. And then at Gorakshep and toward Everest Base Camp and back again, we had a couple people at 6s, and we had one person that was on oxygen. That picture I showed you had an AMS score of 8. And so a couple of people did get it. You sort of see it coming. One of the big questions in high altitude physiology is why, who gets sick and why. We don't really know yet, and so that's some of the background of this that we're trying to sort out. But it's interesting because some people can get really sick and some people really don't. I think it's more important to think really about prevention. So things like ascending slowly, not exerting yourself too much, taking a rest day every 2 or 3 days to sleep at that altitude, doing acclimatizations coming up and back down to sleep lower, making sure your hydration is really good, making sure that you're eating a lot. And I really think if you take care of those things, even without taking Dynamox as a prophylactic prevention, if you take care of things like exertion, sleeping well, hydration, food, and not overexerting yourself, then you can largely eliminate or avoid some of these acute mast sickness symptoms.
Perfect. That's a great answer. All right, next question. What was the biggest challenge or hiccup that occurred on the EBC trek, and how did you adjust on the spot? Also, specifically, what type of security and backup measures did you put in place for data storage?
Yeah, so kind of a two-part question. I'll answer the first one first. In terms of some hiccups. There's probably too many to mention, but it's just something you expect, that things are going to go wrong, and you organize as best you can, and then you be prepared to be flexible, and that's really the best advice I can give. One of the major hiccups that hurt us in terms of the research was one of our Pelican cases. You may have noticed that we had them locked when we left Calgary. That's a mistake, and we had one of them labeled battery. We had a solar-powered battery we brought along just in case we needed some backup power. So we were trying to be prepared for that question of whether or not we had enough power. We were able to buy it in the lodges in the end. It worked out fine. But and so that Pelican case got hung up in Toronto and was not put on the next plane to Kathmandu, and thus it was one of our 5 Pelican cases didn't show up. And in that Pelican case had the battery, which in the end we could do without, but had all of our respiratory gas lines and things like that. So if we wanted to, we put it all in one bag to make sure we knew where it was, and it was all in one Pelican case that didn't show up. So when we flew up to Lukla, we only had 4 of our cases. And so because Nima is such a star and is so well connected, our lead guide, he had someone meet the Pelican case 2 days after we left at the airport, because it finally got sent along with lots of emails between myself and Air Canada while in Kathmandu. Lots of bags didn't show up either for people's clothing, but eventually they worked out. And then grabbed the bag of respiratory gas lines and other things like that, took it over to the municipal airport, had it flown up to Lukla, had a porter run down, meet it at Lukla, grab it, and run up to Namche in a day, which usually takes us 2 days. So we had it that night in Namche. Too late for our daily measures, rest day measures that day, so we had all the respiratory stuff up higher. It didn't hurt the RSA studies, but it certainly hurt many studies where we wanted to play with gases. And so that was a major hiccup that we had to be really flexible around, working around.
Perfect. Very good.
You asked also about data security.
I was just going to say, yeah. Jump
so maybe
into
I'll just
that
mention
as well.
that. Yeah, so in 2012 when I was there, we spent 3 weeks of 5,000 meters or so at the Italian Pyramid Lab, and we had lots of laptops, hard drives go down, and even USBs, like 1 terabyte USB storage hard drives go down as well. So it's just something probably to do with the atmospheric pressure that causes leaks and seals and hard drives go down. So we knew that, and so we made sure we had lots of backup laptops. The software installed. We wanted to make sure we had we had something like 6 external hard drives to back up data on, and a lot of our data was recorded in paper binders, in duotags, so that we could write things down and enter them online afterward. And so between the data that we could, we'd write down with a pen and paper, and data that we had to archive, say from LabChart, we backed up multiple times on external hard drives, and we left all those laptops and hard drives in fair shape, 4,200 meters, to make sure that taking them up high needlessly would put them at risk of failing. So we did think ahead about that, and in the end, nothing failed in terms of computer hardware or software.
Perfect. Very good. A question from Sarah Harding. In your ascent-descent profile in Nepal, it showed that cetazolamide was taken.
Yeah.
Did all participants take a regular dose, and did that affect your measurements, results, or statistical analysis in any way?
That's a really good question, Sarah. It's something that we thought hard about. So I've got participants that are self-funding their way on this trip, and so I have to balance the needs of having a clean data set that's not confounded by lots of variables and the safety of my participants. And so I decided this year that everyone was going to be on Diamox. Everyone took it 125 milligrams twice per day, so 250 per day. That's the lowest prophylactic dose. So it was a low dose, but everyone was on it the same amount all the way up until we got to Gorakhshep, and then we stopped taking it. And so all of our ascent data is confounded by this drug that causes a metabolic acidosis, which is actually protected because it helps you breathe more and protects you against AMS to some degree. And that is a caveat with some of the data on this trip. I'm planning on going again next May as well, And just in talking with other collaborators who have more experience with this than me, we think it's probably safe to ascend to Farish without Diamox, and then as we go higher, we'll probably start it. Again, using all those sort of prevention measures like going slow, taking rest days, good nutrition, good hydration, minimizing your exertion, and those things I think are the big risk factors. So it is a caveat, but the other thing about field work is you can't, there's things that you wish you could control that you would normally in the lab, but you can't in the field. Diet has changed, you're jet lagged, half of you have Trevor's diarrhea, the other half will have it tomorrow, and so that causes an acid-base imbalance as well. So there's all kinds of caveats with this kind of work, and those are the choices you have to sort of make is balancing off your data and safety and feasibility of the work.